Hi, I'm Peter Brickerts, Tech Art student at Breda University. Recently we've had the opportunity to show some of our work at the Houdini Education Hive, where another student and I presented a track generation toolset. I've since received a few questions, particularly regarding the viewer state and the intersections. Both would be too large topics to discuss in one video, so in this video I'll just focus on the viewer state. Perhaps I'll make a video about the intersections in the following weeks, but for this video you should have a basic understanding of Houdini and Python, and we'll also use a minimal amount of vex. So this will be the final result. You'll have this curve that sweeps a line and has these handles that allow you to change the banking and scale the individual points. So let's get started. I'm gonna create a geonode. And that I'm gonna create a curve. So this is gonna be the curve that we use for experimenting. I'm gonna scale out a bit here and just hit enter, and this is gonna be our simple curve. Then the sweep, and we're gonna sweep a line. This line I want 3 points. Direction -1 there. This one. Paste the relative references divided by 2, and now we should get a decent sweep, although probably a good idea to set the op vector, so at op equals set 0, 0, 1, 0, and polyframe that makes and the tangent. And of course I'm stupid, but yeah, now that works properly. Now a resample, and I'm gonna set this to interpolate curves. Now you could so let me show, probably better if I do this and then that. So what you see now is the black line is the interpolated one and the white line is the actual points. And we're gonna place the handles on the actual points. So interpolate is better in that sense because the black line still goes through the points, so the handles won't be offset. You can set it to subdivision, but then the handles won't align properly, but your end result will be more smooth. Ultimately, it's a decision of what you want. We'll go with interpolating curves for now. Now, the other thing that we can already do here is essentially add the handles. So I have a FBX for the handle that I'm gonna load in here with a file node. So this one. And of course it's absolutely huge because I made it in Blender, but yeah, one good trick, you can lock this node, and then it also works in an HDA with like, or for people that don't have access to the FBX on that, right? So because it's huge, I'm gonna transform it. 0.005 should be decent, and then copy to points. We take the output of this polyframe and put this in there, and of course we're gonna take the output of the curve and put that in there. And now of course there's not a polyframe on there, so I'm gonna put one there, and now I can merge this and this. Now this is turning black because it doesn't have normals, so I can add a normals node there. Also because I imported this as an FBX, there is a lot of useless attributes, so I'm gonna delete these. So point attributes, we want everything except for pgun demon. Yes. Okay, so we got that working. And now one thing I want to do is when the user is in the banking mode, I want these banking handles to be green and the scale handle to be gray. And when the user is in the scaling mode, I want the opposite. So I'm gonna add a color node here. And I'm gonna plug this in there. And essentially I have a primitive attribute on here that is either half circle, scale, or banking. And so I want on the left the at scale to be, well, some shade of gray. Maybe that's a bit too dark. That seems good. And then another color node, and here at name equals banking and color green. Sure, I don't know, that one seems fine. Copy paste here, and essentially here I just need to invert the colors. So to identify the gray, I'm gonna do this and then switch the other one. So now I can switch, and we don't have a value to switch this based on for now, so it'll just go to the default, but we will have the value for that in a moment. Okay, so now we have a basic setup here already. So I would say we can make this an HDA. So I'm gonna create new digital asset from selection. I'm gonna save this on my desktop. Well, banking and P scale or something like that. Banking and P scale. Well, not PP scale. Yeah, seems fine. Okay, so one thing is we need two outputs because actually I'm gonna set that up right away because we want the handles and the geometry both to be visible on the main output, but we want a second output with just the geometry of the track, right? So I'm gonna create an output, and this is gonna go into the first output, and then the second output is just gonna be that. So we got that figured. For some reason there's an error. Why is there an error? Collecting output node with the same, oh. Yeah, that's stupid. Now that works. Okay. Well, so we have that. Now we can add in some parameters already. So we will get the, oh, not a float, it will be an int. So that's going to be our shift parameter. So when the button shift is held, I want the to switch between the rotating and the scaling mode. Also, we need a string because I'm gonna get the data from the viewer state into the subnet by using Json. So I'll just create a string here that, oh, didn't add a label. Didn't add one here either. Well, okay, and finally, gonna add a button and call it reset. We can go to interactive, and this is essentially where you create viewer states. So I can just go to new here, and this gives you this cool window. And what's really cool is you can click on these boxes, and it's going to create some basic functions for you. So we need on-key transit event, we need on-mouse event, and on enter would be a good idea. So I'm just gonna hit accept here. So first I'll go a bit through what each of these functions does. And then we'll start coding in here. So essentially here we have the class. So the viewer state is a simple Python class. You have the init function. So this is the function that gets called when it gets created. So you want to instantiate your variables there. And you can store these variables in self. So then you have access to these in all of the functions, which is really great. Also, well, we have these functions, so on enter, on mouse event, and on key transit event, as we selected it earlier. And you might be confused by Quarks and what Quarks is. So essentially, Quarks is just a dictionary in Python that holds a lot of useful information. So as you can see here, Quarks node gives you a reference to the current node that it's working on, or Quark state palms gives you the state palms, and so on. So you can get a lot of useful information out of this dictionary, and luckily it gets fed into all of these functions. So you can get a lot of useful information, like here, the UI event, all of that you can get out of the Quarks dictionary. Well, and of course you get self always, so you have access to the variables that, well, you need for the entire class. And yeah, down here, this function you probably shouldn't touch because it's there by default. Yeah, you don't need to change anything on that. Well, one thing I'm going to do right away, because we'll need it later on, is import Json. Oh wait, actually, probably a good idea to add it here where who also gets imported. So, the first simple task we can do is, in the class here, we can create a variable that I'm just going to call MSG, and I'm going to say click and drag to rotate, hold shift to scale. So this is going to be what is shown in the viewport at the bottom when the viewer state is active. And well, it makes quite a lot of sense to set it up in the onEnter function. So yeah, we're gonna put self.sceneViewer, and remember, this is defined in the init function by default, so we have access to the scene viewer. Set prompt message, and then state.msg, because we are in the state, and yeah, it's a variable directly in the state. So if I apply this, and I have this selected over there. Let me make a bit space here. I can enter, and now you see, well, now it disappeared for some reason, but yeah, click and drag to rotate. Oh, it disappears when you go there. Well, that's interesting. Well, anyhow, yeah, now you have that message there. Okay, but that's doing nothing for us yet. So the first thing I think we should do is probably get the shift to work, because that seems like the easiest, well, task in that sense. So for that, we will need this onKeyTransit event function, because this gets called when the user presses or lets go of a key. So we have the UI event here. We have well, the state palms we don't really need, but what we can now do is we can get the node. So node is Quarks node, and probably, oh wait, actually it's probably a good idea to do this in here right away. So here we can go self dot node equals none, because, well, up here we don't really have something to put because we don't get quarks in the init function. But what we can do is in the onEnter function, we can just go, instead of node equals quarks node, we can go self.node equals quarks node. And now down here, we have access to this function. So we need the shift parameter. So I'm going to create a function, a variable here, a shift param that is going to hold that. And now we can get self.node.param, and then I think we named it shift, so shift. And now this variable holds a reference to our shift parameter. And essentially what we can do now is we can check if the shift key is pressed down. So for that we go UI event.device and then is shift key, and if it's equal to 1. So if shift is down or held down, this is equal to 1, and then we want to set the shift param to 1, and we want, actually, yeah, this we also have to create. So we also want to create a variable overall for the state. So I'm gonna go self.shift 0 by default, and then this is gonna get changed as soon as yeah, the user does anything with the keyboard. So alternatively, if shift isn't clicked, we want shift param.set to 0 and self.shift to be 0 as well. So now if I apply this and we go here, and we go into the viewer state, you can see when I press shift and let go, well, in the viewport here, this changes. So now if I could just copy this parameter and I go in here and on the switch, paste relative reference, go up and press shift, now you can see the color switches. So this is the rotating mode, and this is the scaling mode. Of course, I still can't do anything here, but this already works. One really nice window you have is you have where is it? Is it inspector? Yes, viewer state browser. And now if I select this here and I move this out of the way, you can see that we get like quite a lot of logs. Yeah, right now you can see when I hold left mouse button, it prints true instead of false. And other than that, it prints the mouse coordinates. And as you can see, the 0, 0 point is at the bottom left, not at the top left, like it is in a lot of other well, coordinate systems. But yeah, let's continue with this. So let's next work on what happens when the user clicks on something. So the idea is essentially that the user clicks on a handle and moves the mouse to the left or the right, and the viewer state or the HDA then rotates the handle and the track around, right? So we need to know which handle we're clicking on and also from what direction we're clicking on it, because we don't want the rotation to be inverted, but it's different depending on what direction we look at it from. Essentially what we're going to do is we're going to raycast into the scene from where the cursor is, and then we hit the geometry, and we can read the data we need from hitting that geometry. So in the mouse event, we can see what we already have. So we have the UI event, we have a device, and yeah, here we're logging what you just saw in the log before. And you can also, yeah, put anything in the log and check out what's happening if you're running into issues. But essentially, one thing we will definitely need here is the geometry. So it's probably a good idea to get the geometry for the entire function on mouse event. So I'm going to say geometry equals and then self.node.geometry to check what actually happened in this function, because this function gets called when you left click, when you let go of left click, or when you just move the mouse. You can also always check in the documentation for what exactly this function does, when it's triggered, etc. But yeah, essentially we can get a reason for why this function was triggered. So we can go reason equals UI event.reason, and this we can check. So if reason equals and you can see we even get autofill here, thanks side effects. And yeah, the .start one is when the mouse button was just clicked down. We can get the X position of the mouse. So .x start equals def.mouse X. And as you probably remember, we assign a value here to self. So this needs to exist here as well. So self dot what did I name it? X start equals 0. And now we have that saved on the entire state. And there's a practical function which assigns two values. So you have origin, comma, direction equals UI event.ray. And this is essentially we get the origin and the vector of the camera array at the position of the cursor. And what else we need? Well, we need a position, we need a normal, and we need UVW, and we don't really care about any of these. Well, we need them for the function because we're going to use the geometry.intersect function. So I'm going to name this intersected equals geometry.intersect origin, direction, position, normal, UVW. And what this is going to do, it works a bit like the C intersect, or the vex intersect, I guess. So the intersected will get overridden with the primitive number. Origin will be, well, that stays the same, direction stays the same. Position, normal, and UVW get overridden. Now, we don't actually need any of these. We just have to have them for the function. So, now that we have this, we can check if we actually hit something, because if we didn't hit anything, we don't really need to do anything. So yeah, we check if, and we can just do if not intersected equals -1. So we could also go if intersected is not -1, because it becomes -1 if we don't hit anything with the raycast here. Yeah, essentially we can get the prim now. So we have the primitive number, but we don't have a reference to that prim yet. So prim and then geometry.prim and intersected. And now we need to find out what the tangent of the curve at that position is. And currently we don't really have a way to do that. So I'm going to apply this and hope there's no errors. Seems good. And what I'm going to do now is we have this polyframe here, and we copy to the handles, and the polyframe defines the normal attribute as, or like defines or puts the tangent into the normal. But the problem is, while the copy to points keeps attributes that aren't the standard attributes, the standard attributes don't get overwritten to the thingies. And also it's clearer if we give it a proper name. So I'm gonna create this here, and I'm gonna say v at direction equals at n, and also we probably want to have an attribute for the point number, so we know which value to actually change with the viewer state. So I at pt num equals at pt num. And now if we go here and we check the point attributes, yeah, we have direction, we have pt num. And does pt num work also? Yes, it does. So here we can see we have well, it goes from 0 to 3, and we have 4 points here, so that is perfectly fine. Now one thing that should be done here is, no, not a wrangler, attribute promote. So I want to get this attribute from being a point to a primitive, and we want direction and pt num. So let's see if that works. So now we have direction and pt num. Good. So back into the viewer state. So where were we? We have oh yeah, right, we have the primitive here. And now we can get this direction, and I'm just going to call it normal here because more or less it is. We can go prim dot float list attrib value, and we want direction. And now this is a float list. It's not a Houdini vector yet, so I'm gonna go normal equals who.vector3 based on normal, and now it's a proper vector. And now it probably makes sense to also log this and check if the result is correct. I'm gonna apply. So I found the issue. The issue was that I forgot to have these brackets here in the vector3 lines here. And I also removed the other log, so we don't spam the log entirely. But yeah, when I click on anything now and I hold afterwards, we read out these values. And since this doesn't have these attributes, we get 0, 0, 0 there. But if I click on any of these, I get the direction that it's pointing at that point. So that is working. Now let's see. Essentially, what we need to check now, though, is whether or not we're hitting the backside, because that's the whole purpose of getting this normal. So what I'm gonna do is I'm gonna set the angle to direction, angle to normal. So this gives us the angle in degrees between the normal or the direction at the point and the angle that we've raycast into the scene. So that way we can find out if we hit the back side or the front side. So if the angle is smaller than 90, we hit the front, and I'm gonna create a multi, so self.multi equals 1. and else if the angle is bigger than 90, we hit the back, and that means we want to multiply the rotations, or well, edits to the rotation by -1. And well, we use a self here, so I'm going to create self.multi equals 1 by default. And we can also log this, so self.log self.multi, and then we can see what happens. So move this out of the way, enter the viewer state. So when I click anywhere, so that's, well, that's a -1, but so here we click the front side, now we click the back side. Front side, back side. So that's working nicely. So as the next step, we also want to read the PT num. So that's fairly simple. We can just, alright, actually also I can remove the log so we know it works. So I'm just gonna define self PT num, because we're also gonna need this if the reason is another one and we don't directly read this. We need to be able to see what the previous, or well, what was clicked on essentially. When you click and move the mouse somewhere else, we still need to remember what that is, so I need to save it to self. So it's self.ptnum, and that's just an attribute value called ptnum. So of course we don't have that here yet, so self ptnum, and I'm just gonna go -1 here, because that way we then know, well, if nothing was hit, we can set it to -1 essentially, and then we can use that information in other places. So what happens if we don't hit anything? So we need to go here and then else. So this is if we don't hit anything, and then we just set self at self.ptnum to -1. And yeah, that's pretty much it for this reason start. So essentially we want to edit the value while the mouse is moving. So if reason and then event reason dot active, and active is essentially left mouse button is held down, or well, not, but essentially mouse movements is what gets sent to, or what is the reason active. So we only want to do anything here if we actually clicked on something. So if there is a ptnum, so if self.ptnum is not -1, then we want to do something. And we need to essentially calculate how much the mouse moved. And as you might remember, we defined xstart here in the start. So we have this variable that holds the x position of the cursor when the mouse was clicked, well, when the mouse button was pressed down. So essentially we can see if the mouse position changed based on that. So we can make a variable for the offset in x. So we have def mouse x minus self.x start, and now we know how much the cursor moved. So we also need to set the start to the new mouse X, because otherwise we are going to exponentially keep adding values. And yeah, of course we don't want that. So now we need to know whether or not shift is clicked. So we have this self shift variable because we want to do different things based on whether or not the user wants to rotate or change the banking, right? So if self.shift equals 0, this means we're working on banking. And well, I can write banking here. And as you might remember, we made the multi, so we can just offset equals, or times equals is the same as offset times self.multi. So this here is the same as this. And when we have that, we want to find out if there is a value already. But that we don't really know right now because we haven't actually made that. So before we can continue here, we actually have to, well, figure out the JSON part of things. So let's start creating a proper structure for our data so we can read this in properly here. So we're going to do this on enter, and essentially we want to make sure that we have an array that contains information about all our points. And we're going to use JSON for this. And essentially, if you've never used JSON, just imagine it as a transfer for getting your data into a text format and then afterwards reading it from that text format again without you having to manually write some, well, string saving code or whatever. You could also instead use a multi-parm, but I feel like multi-parms are just more of a hassle to set up than JSON is. So remember to that you have to have import JSON here. And yeah, let's get started with this. So what we want to read in here is we want to read the JSON parm. So we have the self node here, and the JSON parm. We're also going to set this to self because we need to be able to change it inside the mouse event as well. So I'm going to go self.node.parm JSON. So now we have and I forgot the equals again. So yeah, we have that now, and we want to have the value of this because this is just a reference to the parameter. We need the value of it. So I'm going to name this self.json. Oh, well, actually, we don't need that in self. We can just go JSON string equals self.json parm.eval. And now that has the actual string in there. Now, we also need the geometry again here, so we can go self.node.geometry, and we save that to geometry. And actually, while we're at it, it probably actually makes sense. Also, there should be a 0 there to save the geometry in self.geometry, and then also geometry none there. And where did we use it? Here. So there we need self.geometry. Here self.geometry. Well, that we don't need. Self geometry, self.geometry. So, where were we? On enter, and yes, here we set the self geometry. Okay, so one thing I want to make sure here is if self.geometry is not none, and then I want to get information on how many points I even have, because that will of course decide how big my array gets. Right now that's not really possible though, because if we tried reading the point number from this now, we would get way more points, because of course the handles themselves also have points, and we resample everything. So what I'm going to do here is here where the input is, I'm going to create a wrangle, and that's also going to go in there, and then this should run over detail, and I'm just going to create an attribute there that is just going to be the amounts of points in this input. So now in here I can read that attribute in. So I can save this as endpoints, and it's just self.geometry dot attrib value handles. So now we know how many handles there are. So I can also print this and see if it works. Let's see. Apply this. And now hit enter. We get a print 4. We have 4 handles, so that is correct. So I can remove this. And well, if there is no geometry, then endpoints, of course, is 0. Now, there's a few cases for what might be thrown at this, right? So, option 1, there's nothing in the JSON string here. Option 2, there is the exact amount of entries in the array we need. So in this case, for example, it would be 4. Or option 3, there's more or less. So what we essentially need to do is we need to go through these cases, and depending on that, make sure that the end result is always an array that has the exact length as the amount of points that we have. So what I'm going to do is I'm going to test if the JSON string, which we read in here, is empty. So if this is empty, then what we need to do is essentially we need to create a list. Oh, I'm sorry, I kept referring to an array. Of course, I mean a list here in Python. But we need a list now with the length of the of the amount of points that we have. So in this case 4. So I'm just going to create an empty list for now. So I'm just going to do list, and then I'm going to loop for e in range, and then just in range of endpoints. So if we have 0 points, then this is going to get no entries whatsoever. And for each point, now you could put in an array here and just, or a list here and just use the indexes, but I like having dictionaries for things like that because it makes it very easy. So I'm going to create a handle dict here. So You could also name this point dict or whatever. So like each control point gets a dictionary, and then I'm going to change the banking to 0 and the handle dict scale to 0, because remember, this is when you start the viewer state. There's no values. What values do you take? Well, 0, 0. So of course we still need to append that. So JSON list.append and then handle dict, and that is that case done. So after this we have a JSON list that works. But what if we do have something in that parameter? Well, then we need to load that data in, and this is where JSON comes in for the first time properly. So we go JSON dot load as for load string, and we have the JSON string, because remember, if there is something where was it? JSON string. Oh, here. So like here we evaluate the JSON string, and here we feed it into the JSON load as function. So essentially what this does is it reads in the information in JSON format from the string and converts it into this list. So now we have a list, and we can find out how long that list is. So now we have the length of that list, so we can compare it to the amount of points that we actually have. So if length is smaller than endpoints, we need to add more to that list. So what we can do is we can add or create an extend list, and then for e in range of endpoints minus length, because remember in this case we have a bigger endpoints than we have length, and this gives us a positive result always. So if, for example, we have 3 points in the list, and we have 4 points in the geometry, this result will be 1. So this loop will run once. What we just do here is essentially do the same thing we did before. So I'll create a handle dict, and again banking equals 0 and handle dict scale equals 0, and then extend list dot append handle dict, and finally after the loop we can add this extend list to the original list we had. So JSON list dot extend and then extend list kind of merges these two lists to each other. So you get the values that you had in the values and in the text, and you get, well, the default values added to the end of that array. So alternatively, if length is bigger than endpoints, and you wouldn't necessarily need to do this, but I feel like it's the cleaner approach to also take care of this. So for e in range and then length minus endpoints, so this is also always a positive number, and then we just JSON list.pop, and if we don't give anything into the pop function, it always removes the last entry. So if the length, so if our list, let's say, has 10 entries, but we only have 4 points, the last 6 entries of our list will be removed. So now we need access to this list in the other functions. So I'm going to say self.json list equals JSON list. And now we have access to this. Oh well, not yet, because I also need to .json list none. And did I self.json palm, but I don't have it up here, so also self.json palm. Okay, now we have that. Just to see how it looks, I am going to go self.json palm.set, and then the function here is json.dump_as to convert it to a string, and we want to convert the JSON self.json list to closing brackets. And now if I apply this and enter here, yeah, there we go. So now I got 1, 2, 3, 4 entries up here, just as we needed. And we can test, for example, if I remove one of the entries, and go into the viewer state again, it recreates an entry at the end. So that is working fine now. So now we can continue where we left off before. So that was down here. So we can continue with the banking now. And essentially, we want to read in the value that is now in the JSON list. So we can create a dictionary here. So pt_dict, because we want this. Well, we want only the dictionary of the point that we're currently working on. So I'm going to add set it equal to self.json list and then self.ptnum, because remember we save self.ptnum here. And then we can get the value that is currently in there. So you can just call this old offset, and that's pt_dict, and remember we called this banking. And we can now calculate a new offset. So the new offset is the old offset plus the x offset that we calculate. And now we can change our pdict. So we can change the banking value of our pdict to the new offset. And now we just feed that back into the JSON list. So JSON list and then self.ptnum. And we want to put in our ptdict that we changed. Also, we want to see live updates on this, so we need to update the parameter constantly when you move the mouse. So I'm going to go palm and then just dump_as the list. And now this should already work in theory. So if I go here, and I'm not sure which point is which, but yeah, so as you can see, when I go to the right, the number increases over here. When I go to the left, it decreases. And this is in pixels. So it's quite large numbers, but yeah, that's not really a problem. We can just scale these numbers later in the HDA. But now for the other case, which is, well, else, and then next we worry about the scale. So for the scale, same thing. We don't need to use the multi here because scaling will always just be the same from both directions. So we just take the ptdict directory and then we get the old offset. And that, of course, is also in the dictionary, but under scale instead of banking. We calculate the new offset, which, of course, is the old offset plus x offset. And then one thing that is important here is because scale isn't really a thing where you want infinite numbers. So you want to cap these values. So you don't want negative numbers. You probably also don't want super small numbers for your scale in the end. However, you want to be able to move the mouse to the left, of course, of the object of the handle and make it smaller. So you kind of need to take negative pixel values, but you want to end up with a positive scale. So what I think is a good idea here is to just assume that you have a range of -1000 to 1000. So we can just go if new offset is bigger than 1000, new offset equals 1000. And alternatively, if new offset is smaller than -1000, new offset should be -1000. So that way the value can never go above or below these values. So now we just set the value in the dictionary to the new offset, and again we put in the dictionary back into the list, and we of course also set the parameter. Okay, so now we have this done. So if I apply this here now, can we... Yes, see, so now the scale also works, and it's also capped at 1000, so I can't go higher or lower than -1000. And yeah, this also works. So of course, it does nothing yet to the geometry, but the values themselves are changing accordingly. So what comes next is actually changing the geometry in the network. So here we are in the subnet, and essentially we are going to import the values now. So I'm just going to create a Python node here and put that in between there, and so what we need to do here is, of course, we need Json here. So import Json, and well, also we need the parameter here. So what I'm going to do is I'm going to edit the parameter interface, and I'm going to add a string here, and I'm just going to name this JSON in, apply, accept, and now I can go up here, copy parameter, paste the relative reference, and in here I can now save this as a JSON string variable. So eval parm and we want python1/json in, and if JSON string is not empty, we want to create a JSON list, and we want to load in the string. So now we essentially have the same data that we had before in here. So if I go print JSON list, we get the same list that we had before. So that's why JSON is really cool. You essentially, just make all the stuff you want to save a single string, and you can load it back in here. What we want to do next is essentially we now have this list that has an entry for every point, so it makes sense to just loop over all points in our geometry. So for point in geo.points, and we have geo here by default, and then we need the number we're looping over, so that is point.number. And now we want to read the value, so ptdict equals json list and then ptnum. Now this probably works in most cases, but if the JSON list is empty, or well, there's like this is out of range or something like that, this will throw an exception and cause an error. So a good idea here is to put a try and then an except and then a break. And what this means is essentially try reading this value. If you can't read it, stop this loop. So then if there's no JSON list, so like the field is just empty, it's not going to throw an error, it's just not going to do anything. Well, which is better than causing an error, of course. So we want to get the p-scale and we want to get the rotation. So I'm going to say p-scale equals ptdict. Want the scale. And now we have a value between 1000 and 1000, and we need to map this to positive values. So I'm going to say p-scale equals, and then p-scale plus 1000 divided by 1000. And of course this in brackets here. But what this is going to do is it's going to map our value from -1000 to 1000 in between 0 and 2. And now I also want rotation. I'm just going to name it prot. And this is saved in the dictionary as banking. And this value is also, like, we have huge values, so we definitely want to go down here. So I'm going to divide this by 1000. So our angle, the pixel value in movement will be divided by 1000. Keep in mind that this is in radians. So 1000 pixels then means the value is 1 radian, half a circle. That's fair enough, I believe. Well, and now point set attrib value, because we want to save these as attributes on the point. We don't want to actually rotate the points here in Python. You could do it if you want, but I'm going to do it in Vex instead, so I want to save it to an attribute here. So attribute prot, and I want to save prot, and point.set attrib value p-scale, comma p-scale. Okay, and now this is going to throw an arrow. because we don't actually have these attributes. So you could create them in Python there, but I feel like it's way easier to create them here in a wrangle. So we want f at p scale, and the default there we want 1, and f at prod, and the default there we want is 0. And also I'm going to define up already as 0, 1, 0. Okay, and now in here, oh yeah, right. Still throws an error, because it, for some reason, doesn't know that the values we have here are floats. So I'm going to make sure it gets converted to floats, and now it doesn't throw an error anymore. So now we have this problem solved. What we need to do next is we need to do the actual rotation. And for the actual rotation, we're going to put down an attribute wrangle. And in here, I am going to get the angle that we want to rotate. Remember, it's in radians and not in degrees. So float angle, or I'm thinking of it at least in radians. But f at prod, and we need an identity matrix. So I'm going to create the identity matrix. We also need the vector that we want to rotate around. So our axis essentially of the rotation, and I'm going to use the normal here. I'm not sure, do we actually have a normal? Also, I forgot semicolons, of course. Do we have a normal? No, we don't have a normal here. So probably it makes sense to put this polyframe somewhere here, and then here we have a normal now. Okay, so the next thing is the rotate function. So the rotate function takes in the matrix, it takes in the angle that we want to rotate. Again, this is in radians, and then normalize the axis. The axis is probably already normalized, but I'd just like to make that sure. And then we rotate up by that matrix. And yeah, this gives us the rotated, well, rotate E doesn't really make sense. Rotate up. And then I can go at up equals rotate up. Okay, and now the final thing is, well, actually p-scale we already have, so we don't need to do anything with p-scale there. But yeah, as you can see, now if I go up here, the handle does work. For some reason the geometry doesn't move with it, but that is going to be investigated. Oh, I think it's this polyframe here, right? What is it? So there is, so we have the rotated up vector here. Still have rotated up vector. Here we don't. Oh, yeah, right. Of course, that was not the smartest. Yay! So now it's working, and yeah, we can scale. Now, these values might be a bit stupid, the limits that I set, so I'm going to change that. So in here, the limits, oh, where was that? Here. So upper limit, let's say maybe 5,000, and then 5,000, and maybe not minus 1,000, but minus 500 or something seems more reasonable as a lower limit. I'm going to apply this. Let's see how it is. Yes, that seems, although, yes, okay, so that was the issue. So I can remove this one. So this 1,000 here has to be a float, of course. Okay, but now this works properly, and the rotation works as well. So I would say mission successful. Now the last thing I want to show is the reset button. Doesn't necessarily have something to do with the viewer state, but I just think it's a practical functionality. So for that, we go into the type properties again, but instead of to interactive, we go to scripts, and we can go to the Python module here. And what you can also do if you have the Visual Studio Code or like another external editor for code, is you can open that with edit extra section, source code, and then Python module. But for the sake of the video, I'm going to stay in this editor here. In here, we need JSON, and we need, well, I'm not sure if we need it, but I added, if in case we do, the who module. So we want to define a function here, and we define the reset function, and I'll name it Quark, well, not name it, but as an input, it'll take Quarks, because in this context, again, there's a lot of useful information we can take from that. So we can get the node that we're working on, so Quarks node, which is also the only thing we need. Then we can get the geo of that, so node.geometry, and we can get the JSON parameter with JSON parm equals node.parm JSON. So now one thing we need to check is how many points we have, because when we reset this, we create essentially the same empty list with the right amount of values for the amount of points we have. So we can essentially just copy paste this from the code of the Python state. So we checked that here in on enter, so we can just copy this, paste it. So now we have endpoints, and once we have endpoints, we essentially create this JSON list. So we now have an empty list. We loop through the amount of points that we have, and on each for each point we create a dictionary with banking value 0, scale value 0, and we append that to the handle dict. Oh wait, no, we append the handle dict to the JSON list. And once we have that, we have the proper JSON list, so we can just say JSON parm equals JSON.dump s of JSON list. Oh, of course. it's not that, it's set json.dump as JSON list. Okay, now that is correct. Now we can apply this, and now we need to set up that on this reset button, when you press it, it calls that function. So essentially, we just go to this field here, the callback script, and we put in who.pvw.hm.reset, and then we feed in quarks. When I apply this now and accept and hit reset here, well, we get an error. So Python module line 11. Okay, type properties, script, line 11. Oh, yeah, of course. That went wrong when copy pasting. Now when I apply this, global name self not defined. Oh yes, of course, if geometry, and then also here, geometry. Well, that what happens when you're lazy and you copy paste. Reset. Global name geometry is not defined. Oh yeah, of course, because it's called geo. Well, geometry. Don't be lazy. Now it works. Okay, right. So now when I'm in the viewer state here, I can edit everything, and with a reset I can reset it. Alright, awesome. So that's that then. So thanks for watching. I hope you could learn something, and if you have any feedback or questions, just leave them in the comments or message me on Twitter, and good luck.